So, good afternoon, everybody. I'm Thomas Ludwig. As all the others, I thought I will make a short review of what I did in the past tool-wise. The steps of the career are Munich from '88 to 2001, then Heidelberg from 2001 to 2009, and now University of Hamburg. And for those who don't know it, currently then also head of the German Climate Computing Center in Hamburg and professor for computer science there too. Okay. When I came to TUM in 1988 together with Professor Arndt Bode. Oh, by the way, Arndt Bode was invited here and I had a meeting with him last week, a virtual meeting, and he asked me to please tell all of you his best regards. Unfortunately, he was not able to make it. So some other obligations or whatever. He would have been happy to join us, but it was not possible. So I went with him from the University of Erlangen to Munich and started with a PhD. And at the time when we arrived there, we already had one person being there, Thomas Bemmel, and Thomas had developed a monitoring tool and a debugging tool for real-time programming. The thing was called RealBug, and it also had a hardware monitor component. And starting from this, we developed tools then in the 90s, beginning in the end 80s and then 90s. And in the 90s, we had a tool environment with debugger, performance analyzer, program flow visualizer, load balancer. Then also we had a deterministic replay component, things like that. Everything was made for the IPSC parallel computer from Intel that we had at the time. And then also in the mid-90s, we made a port to Transputer system from Parsitech, also sold it to them. So it was quite good. And for the Intel, that was with a hardware monitoring component. And we had such an intermediate socket that you could plug the processor in on top and then plug that to the motherboard. And we even used so-called bond-out processors with additional pins where you could get additional information. The reason was Intel was in Munich and Thomas Bemmel had quite some cooperation with them already. So we got access to special processor versions. Then in '95 and later after my PhD, we did this thing that was called Interface Definition for Interoperable Tools, OMIS, and then a monitoring system for that, OCM. Now everything was in software, no longer hardware components, and the main actors, the head of the group were Roland Wissmüller, who is a professor in Siegen from that time on more or less up to now, and then myself. My research was for the PhD, not directly in the tool field, or let's say it was more an automatic tool. It was on automatic load balancing based on process migration. And of course, here we had an online performance monitoring component for the decision making when to migrate the processes. Then the habilitation thesis was on this environment with OMIS. And then in addition, more or less '95, I started with some research in the field of storage. So we had a library that did an emulation of what Intel had at the time for the IPSC, and we produced that library for Sun workstation clusters such that you could do a full development of IPSC programs on a workstation cluster and then bring it to the Intel environment. That is a slide from '95. And slides were still in portrait mode at that time because we copied that to transparencies and you had an overhead projector. Yeah, that was not this landscape mode. And this is how it looked like. That was the tool set that we were developing. Everything was based on PVM at the time. And then we had debugger, performance analyzer, visualizer. We had this thing called determinizer that was for deterministic replay. And then the load balancing component. So we could also we also had a checkpointing component that allowed us to do a process migration on some workstation cluster from one node to the other. That was pretty cool. Together with the checkpoint generator. And also we supported this emulation of the Intel parallel file system. Then when I went to Heidelberg, I continued in the field of tools, but with more concentration on I/O. And I show you some slides of talks that we had at that time. So what we produced was a tool that integrated traces from the client and from the server environment to better understand what's going on in I/O environment. So we had the traces of these two types of activities, client and server. And then of course, the tricky thing are just the arrows between them, the causal relation, which activity on the client side triggers what activity on the server side. And we did that for MPI-CH2 and for PVFS2. And that is, okay, I'll come to the screenshot in a moment. So the idea was to generate the traces for the servers, generate the traces for the clients, then add the arrows from the MPI-IO calls to the corresponding server activities, and visualize everything together in JumpShot, which is provided in this MPI-CH environment. So this is how it looked like. So you had timelines for the clients, the two upper ones here, and you had timelines for the server. And for example, you have MPI file write operations here, and then you have trove operations from the PUFS. This is just the low-level write operations to disk. You have them here, and then you can see which write was connected, which write in the program on the program level was connected to which write on the client-side level. Because the problem was always, this is a more complicated example, the problem was that up to that particular moment, you just had tools that showed you what's going on the client side. So you had the upper 4 lines. The upper 4 lines said, yeah, there's something going on. Then you do a file open, and then you do an MPI write, for example. And what happened with the tools is that you just say, okay, the MPI write, it lasts until this point of time, yeah. It's too long, but nobody understood where the time gets lost. So with the combination, with the traces that we had from the server side, you could do the following. You could see the metadata server, so the MPI open triggers metadata operations here on the metadata server. And then you have 4 data servers. The 4 data servers, for example, open the file, and then you see what the servers are doing, and green is for server activity in general, and the brown one is for writing to disk activities. So what you could see here was that you have issued an MPI file write on the client side, and that triggers write operations on the server side, but they are somehow not balanced. And you found several problems, for example, with the PVFS tuning operations that they had in Roma.io. So Roma.io has this 2-path protocol. It has data sieving, but on various locations in the code were some problems with how they do the tuning. And with this tool now, finally, you could see what's going on, and then you could start to make some correction. Okay, finally, of course, we stick to the, let's say, advices of our senior members, yeah, where David Bailey once said, if everything fails, just show videos and pretty pictures. This is what we did, basically. Then in Hamburg, I still continued a little bit with the focus on I/O with the tools, but then also we had a project on energy efficiency, so we integrated also measurement options for energy consumption, such that you could have an integrated visualization of what's going on the client side and on the energy consumption side, on the hardware. But then the focus of the group shifted, and we did more work in the field of I/O itself. So evaluation of I/O performance, then compression, lossy, lossless, things like that, improvement of metadata performance. These are the things that I did in my group. The 2 people that were very active, Michael Kuhn and Julian Kunkel, they are now professors by themselves, and the group shrunk in the last years. And as I still have only another 3 years to go, so there's no real plan to extend the group. But there's one thing that I would like to speak about today, and this is this issue of reproducibility. And I will switch to that slide set now. Because before I came to tool development with Bode in Munich, I made my master thesis in the same laboratory where Bernd also worked. And I had a thesis that was a parallelization of a fluid dynamic code. And at that time, I was not aware of it. There was a problem with being deterministic. I mean, the code was not deterministic, but if you had a small number of processors, there was not a problem with that. So you ran it 10 times, you got 10 times identical results. But if you had, as Bernd said, we had these 25 processors. If you used the full range of it, then for each program run, you got a different result. And then I always called the physicists and said, look, I have this result, can this be true? And they said, yeah, that is true, no problem. But every night I got another result, and always they said, yeah, it's true, no problem, don't worry. And I was close to a nervous breakdown because there was always, the distribution of the particles was always different. let's say the aggregated values and variables, they were okay, but in detail, it was really terrible. And it took me something like 2 weeks or so to find out that that was the normal behavior of this program. So it had this non-determinism in it, in the code, because I, not knowingly, of course, integrated it. And after having understood that, it was easier to handle it. And this problem of non-determinism and of bitwise reproducibility follows me all these years. And yeah, it again came up, and this is what the talk will be about, in 2015 when I was at the supercomputing conference, and they had an invited talk by Victoria Stodden, who at the time gave a first plenary talk on reproducibility issues and termed that credibility crisis, because there were lots of publications in newspapers, on journals about that, in particular in Nature and also in other publications like Los Angeles Times. It was more at the time about non-reproducibility, for example, in medical science, or what the psychologists did. Yeah, they just found out that the experimentations that they did were hardly reproducible. If you would like to verify the result, that was very problematic. But of course, they found out, or they saw that that also refers to everything that works on a computer, and in particular on HPC environments. We had, by the way, before Stodden's talk, sometimes workshops on reproducibility of a group of people who always did that on the Friday of supercomputing conference, but the reproducibility was more than in the field of bitwise reproducibility, compiler issues, library issues, and things like that. And Stodden started to discuss it in a more, from a more wider perspective. So she said, well, there's something like empirical reproducibility, statistical one, and of course then the computational reproducibility. Not immediately speaking about HPC, but then also about HPC in the later time. So if we look at what's going on in this field, we can distinguish several levels of abstraction where reproducibility is a problem. So you might speak about finding the same insight, that someone makes a research and another group would like to replicate the research and find out whether that was true or not. And then the question is, can they replicate that particular research? A second point is a little bit lower, that you say, I had a program run and I have a description of that and I give it to someone. Can another person reproduce what I did? Maybe on my machine, yeah, such that the environment is okay, that's it identical, but will another person be able to reproduce it? And then on the lowest level, what I was always called, or what is called bitwise reproducibility of a single experiment. So you run a program, you get a certain result, you run it for the second time, and you would like to have it bitwise identical. Is it possible or not? We will just see. Is it necessary or not? Difficult to say. So these discussions here from Stodden and in the world in general about reproducibility coming up in the late 10s triggered also activity in ACM groups. And ACM set up a paper and they did some kind of definition of technical terms and things like that. So in this currently, because they changed it at one point of time, now the current version 2020 of the terminology names it in the following way, that they say, okay, reproducing a scientific result, that's what we call replicability. So it's a different team, a different system. Then we have reproducibility, different team, same system. And we have bitwise reproducibilbility, what they call repeatability, same team, same system. Because
so do they quantify the difference between reproducibility and repeatability?
No, there's no quantification for that. It's just now to get the technical terms right, because everybody was speaking before that. Everybody was just naming it reproducibility, and it was a complete mess in these papers. All different levels of abstraction people talked about, and now they try to sort that out. And there is more going on now, because we see more and more workshops and conferences really concentrating on reproducibility as a general term, and then diving into the issues here.
Because the middle one is really fungible.
Yeah.
If you run the simulation and it says we're all going to die on planet Earth, that's reproducible, but it could be the quantitative aspect could be radically different.
we will not just discuss this today. I will concentrate on the lower levels. But there's a lot of activity going on there, and it's really exciting, in particular from the point of view of theory of science or philosophy of science. I come back to that point later on some slides. Triggered by all these discussions about reproducibility, the Supercomputing Conference series started also with this reproducibility contest. They integrated that into the student cluster competition. So they gave then also students a paper with its results and the programs and said, yeah, please reproduce that and check whether this could be done or not. This is an activity that goes on until today, which is quite popular and quite necessary for the students to learn about that. Learn about reproducibility issues early in their career. That's not necessarily about Bitwise, of course. Yeah. So let's speak about climate science, speak about my customers, so to say, from the Climate Computing Center. So the holy grail of climate science, modeling, what will it be? Yeah, Bitwise reproducibility, of course. Yeah, that is what they always speak about. We will dive into the details in a moment. This is what the computer scientist says about that, because we will see, is there a chance to have it? Yeah. If yes, how much does it cost? Nobody knows exactly. Well, we had last year, by the way, with the NCAR people, organized by a person from DCARSET and one person from NCAR, we set up a nice workshop that took place before the Supercomputing Conference. We made it in Boulder, and the topic was a workshop on correctness and reproducibility. Slides and recordings are available, freely available, so it's quite nice maybe to look at that for those of you who are interested in this. That was a pretty good workshop on that topic. So why do we have these problems here with climate science? The point is, if you look at climate science, this is always highly nonlinear mathematics. That is really tricky because small changes of the input value might trigger big changes of the results, whatever. And then the simulations are usually over a long period of time. So every single rounding issue, not necessarily a rounding error, but a rounding issue, will add up because you make simulations over 100 years of simulated time or so. And that's problematic. So from the computer science point of view, we have, of course, the situation that the associative property does not hold. That means A plus B plus C in brackets and then A plus B plus C might result in a slightly different result value with the last digits. Not necessarily, unfortunately. So there might be non-determinism, but with the numbers that you choose or the numbers that you have in your program, it might not be visible, whatever. And that comes, of course, from the fact that the number presentation in a computer is limited and that you have to do rounding. And unfortunately, that means that whenever you change the order of mathematical operations in your code, whatever you do, if you change the order of mathematical operations, you might get a different result. Not necessarily will you get a different result. So that was just my diploma thesis. Yeah, in some situations, it was just not visible. The non-determinism was inherently available in the program, but it did not show up unless you had a higher number of processors and the timing restrictions were more tight or whatever happened then. No. And sometimes, by the way, machines are also non-deterministic. That refers in particular to the processors. So if we look at bitwise reproducibility, what might harm the chance to get a bitwise identical result? Essentially, whenever you touch the machine and do something, you might change the order of the arithmetic operations, and then you might get a different result. So, for example, you change the... Yeah?
Maybe I make sentences.
Yeah, let me just come to the end of that one. Okay, you might have a different processor, you might have different libraries, you might have a different compiler, or you change the options of your compiler, you make your domain regions differently, you have a different number of nodes, or you might have non-determinism in libraries, for example, reduction operations, or you might have non-determinism in programs for example, load balancing. Yeah? So that is a list. The list is non-exhaustive. And the list is non-deterministic, of course. Speak about
it. People are moving away from IEEE floating point standard.
Yeah, it's the same thing.
Yeah, so
even the standard is not identical on all the machines.
Right. There's differences, but even worse, we thought we had converged on this great standard.
No, we did not.
But now people are diverging again.
Right, right. Yeah. So if you look at that from the...
So, if you don't change anything in the steps until you compile and you have a binary code, you run it multiple times, right? So I understand if you actually have a distributed machine, the message order could be important, right? So it might not be non-deterministic in that case, right? But if you have just one processor, what would be an example that even in this situation you get non-deterministic?
If you have one processor and several processes, for example, yeah, then you might get non-determinism. Because the timing behavior of what the scheduler is doing will never be identical.
Yeah, but I mean, again, this would be reductions, or is there anything else?
Yes, and with the reductions, in the end, it all boils down to one situation. It's the receiving of messages. If the receiving is made non-deterministically, in particular, what you do if you have a non-blocking receiving, where you say, yeah, send me your partial sums and I will add it up in the end. And then you get it in different timing orders. Yeah? Timing comes in, changes the order, and you said, I have a non-blocking receive, and I will just get the values in the order as they arrive, instead of I will add up the values in the order of the ranks of the senders. Yeah, it's just this particular situation that produces the problems. But you never know where it's hidden, because it might be hidden in the implementations of reduction operation libraries, for example.
So it's parallelism is a problem, right? If
yeah.
I have a sequential code, just one process, and I run on a processor, I mean, these processors are quite fancy, but I think it will be determined.
No, because with the new compilers, it's not like this. I will show it.
I don't recompile.
Ah, okay. Yeah, then it should be. If you don't recompile and if you don't have these critical compilation options that make the processor behave non-deterministically, if you don't have this, then it will be deterministic.
Processors age and processors are subject to environmental impact. Processors age and they're subject to environmental interference. Even if you're miles away from the Earth in the vacuum, you're subject.
I've not this in my examples, but this might be an issue too, yeah. Okay.
Processors have no age. If you run a processor for years, that will suddenly fail.
And it's even worse. So Intel, for example, has aging mitigation built in and will dynamically change your frequencies if it ages too much. And I can talk about this tomorrow.
Yeah.
This is already reality.
Yeah. So we can not even in this situation we can fully guarantee it, which is really terrible. So here, speaking about the groups of people who are involved, yeah, this is our responsibility. This is the responsibility of the scientists. So whenever it comes to IPCC computations, they approach us and say, don't touch the machine. No updates in the next year, because we need it unchanged for 1 year for running all these IPCC codes. Of course, we cannot do that. And the scientists themselves, they say, well, we don't know exactly. Maybe the library operation of a reduction operation or the library that I integrate into my code might have non-determinism. So I do the following. I kick this library out and I implement it on my own. And you may not be aware of the coding qualities of climate scientists, but they are very low. So if they implement it on their own, then it's very, oh, this is recorded, huh? Oh, okay, anyway. But if they implement it on their own, then the problem is it's slower. Unfortunately, nobody at the moment, I mean, they're not to blame about that, but nobody at the moment did an investigation about how much it costs us to have the slower library versions that are deterministic in usage instead of the optimized one that might be non-deterministic. Yeah, there's no investigation about that.
Have you guys or anybody else done a survey of which of these ones, how often each of these categories come up as the source of non-determinism?
No, unfortunately not. Not yet.
It'd be interesting to know which of these.
That would be, yeah, that would be cool.
Worried about.
Yeah. because I had some proposals on that. Unfortunately, they were not successful. This is one thing that we wanted to do, because that is very important to see, to quantify these things then.
Yeah.
With respect to the list.
Yeah, that's too bad it was quite fun.
Okay, for climate modeling,
Just one comment. So even if you had a deterministic system, so this would just choose one execution order out of several possible execution
Right.
orders. So there's no, you cannot be confident that this is the best execution order. So this result would be reproducible, but it would not be better than any of the other results.
right. Let's come to that point later, because I will come back to that. That's a different topic, but that's the problem is there are several different topics that are all under this hood of reproducibility. And unless you somehow sort that out, all these details, you will not really understand what's going on there. So let's come back to that in a moment.
Can you also ask one more question? Because the scenario you brought up, I mean, do we have to worry about that? It's clear if you replace the processor, change the compiler, they can have a significant impact. But what Michael said, you don't recompile, you use the same hardware, maybe it has a different temperature. What's the difference? Are we talking?
I will show you.
1000%? Or is it?
It's unclear. It's unclear because nobody did up to now a quantitative analysis of these things. But let me just continue a moment and then we come back to it. So speaking about climate codes, for example, one important code for us is the icon code. That is the so-called working horse. Now by the way, they now provide that open source. They started with that 1st of February. Other groups can download that, can contribute to it. A huge code developed over many years by several groups, in particular by the Max Planck Institute in Germany, in Hamburg, excuse me, and by the German Weather Service, DWD, in Offenbach, but then also with Karlsruhe and some Swiss colleagues and also DKRZ. And for ICON, they have a requirement that they write the code in a way that it's bitwise reproducible. I think, I'm not 100% aware of it, I think they can switch some of these requirements off if they make production runs. But in fact, it's programmed in a way that it can also be produce bitwise reproducible programs, results, sorry. The problem is, for example, when it comes for us to buying a new machine, because we give the vendors some benchmarking programs. For example, the most important thing is icon. So we give the vendors icon and we tell the vendors, yeah, please show us how fast icon on your machine is. What vendors do, of course, is that they use their own compiler with their own options. And as a necessary result, the computational results of their icon runs are not identical to what we gave to them. And then it's not easy to find out whether what they did is correct or not. Yeah? Because you need scientists looking onto the results and evaluating that, whether this is a scientifically valid result. So in the process of procurement of a new machine, this bitwise thing is really a problem for us. So everything has to be checked. And I will show you how these different results might come into existence. So we made a comparison with a compiler, and we did that on DKRZ. So we have the example that a vendor uses, for example, O2 and O3 with vectorization, without vectorization. I will show you what will happen. So we have two situations that we distinguish, two examples. We compare minus O2 without vectorization and minus O3 with vectorization. And then we have several runs of a code that uses also AVX and FMA and dynamic memory management, which makes the processor definitely behave non-deterministically. That was published in a short paper that we had in Springer. So what you see here is a result of the comparison of the O2 without vectorization and the O3 with vectorization. So if you give the code to a vendor and then the vendor says, look, I have a nice compiler with interesting options. And of course he advertises that he says, yeah, that is much faster. Yeah, you need 10 minutes, I need only 8 minutes on my new machine, that's much faster. So the problem is, what is the difference in the results? And I tell you what the graphics mean. So this is the globe in rectangular shape. It's the 360 degrees around the equator. So this is the equator, and the 180 from the South Pole to the North Pole. The color coding means you take 1 square meter on the ground and you compute the weight of the vapor, of the water vapor of that column. Yeah, so that goes up to something like 80 kilogram for the dark red ones. So that's just a color coding of how much water vapor is on each square meter. And this is the result of 100 days of simulation without vectorization. Has a certain graphical representation, yeah. And this is the result with vectorization. And you see, yeah, it looks similar, but it's not identical.
This is frightening how different this is. And this is a great slide. Yeah. It's a terrifying slide.
And in particular, if you are in Obergurgl, for example, yeah. Obergurgl, 46 degrees north, 11 north and 11 east is that point here. So with this calculation, it's this medium blue, and here it's this very light blue. So vapor color, the vapor has a completely different weight on that location.
And we're trying to figure out when the ocean circulation current is going to collapse. And this kind of difference could be which decade?
This is, of course, a task for the scientists then, because then the scientists have to say, okay, if you have these problems here, then I run it 20 times and I have to do an analysis what the scientific truth of all these different pictures could be. Complicated. The problem is, of course, the political one. If you go with such a, with this video, for example, to Mr. Trump, and then Mr. Trump will say, well, if you are not able to really reproduce a single result, please come back once you can do it. And otherwise, I don't believe in what you do. So this is the comparison between vectorization and non-vectorization, just to show you that after 100 days of simulation, you have a different result here. Say it again? Wasserdampf, yeah.
But is there any way, for those results to figure out which one is correct? I mean, there's a difference, but do you have any clue?
The scientists are able to deal with this problem because the scientists, they compute it several times. They have several pictures. They do a statistical analysis of the variance of the pictures, things like that. I will come to another example in a minute. But it's a complicated thing. Yeah, it's not easy.
If the faster one is actually more accurate, right?
Yeah, that would be super good. But I doubt that this will ever happen. Felix?
I mean, this also raises the question, how accurate is reality?
Of course, I mean, this is modeling. Yeah. As my people always say, all models are wrong, some are useful. Yeah, and then, right?
After 100 days, you know which one is right.
There is no such thing like a right model.
But you know what the weather is or the climate is or not.
Yeah, more or less everything is statistics. So let me come back to this in a moment.
Water pressure in every square meter of the Earth to validate this model?
In 100 days.
In any
yeah. Okay, let me just continue, and then I show you some more aspects, and then we come back to the discussion. So that is the comparison between vectorization and non-vectorization. By the way, just to mention this, if you run this configuration 10 times, you will get 10 times the same result. If you run this 10 times, you will get 10 times this result. So it's deterministic in itself, yeah, but the ones are different. This is no longer the case for the next example here, where we say we have this AVX vectorization, non-deterministic behavior of the processor. So we made 4 runs. This is run number 1, 2, 3, 4. They're all a little bit, they look pretty similar, but they're all a little bit different. So that means if you run the program 4 times, and just keep in mind that you wrote a program where you said, I did not enter intentional non-determinism. I wrote a program that is deterministic. You run it with this compiler options, you run it 4 times, you get 4 different results.
Is this due to AVX?
Yeah. And the processor does some kind of reordering, whatever.
Because AVX has a huge amount of out-of-order execution and dynamic scheduling of functional units.
Yeah, things like that, yeah. I don't know the details of this compiler issue, sorry. But it's used
to... I'm talking about the Intel processor.
Yeah.
I mean, once you get on AVX, you have, unless you explicitly synchronize, you've got these different functional units.
That means, of course, you can control these things to a certain extent, but then you will not have the full speed. You can choose what you want to have. So 4 times a different result. Okay, let me just come back, or let me just continue with this difference between climate and weather, because I was not aware of it. Most people are not aware who are not in this field. Weather is just what's going on there, and climate is the 30-year statistics of what happened. So climate cannot be observed. Climate is a mathematical construct. Yeah? So the question is, of course, as climate is the statistics of weather, maybe the problem disappears if we make these statistical analyses that we have integrated into climate science. Yeah? We make weather prediction, it's different to climate science. And I will show you another example that a friend of mine did, and with this example we investigated the following. In climate science, I don't know about the other modeling sciences, by the way. I think there are similar scenarios sometimes. They have one thing that they call ensembles. With the ensemble, they do the following thing. They run a program, you get a result. They slightly change either the input values or the start moment of the simulation, for only a little bit, and run it again, and you get a slightly different result then. And then they do this 20 times. Of course, 20 times the electricity of all that. They do that, for example, 20 times, and then make a statistical analysis of all the variations of all these 20 results. And why do they do that? They do it for some kind of uncertainty quantification of their numerics that they have in the program. Also to get some insight into the robustness, numerical robustness of that. And also, if they have the ensemble mode and run it 20 times, they often get more accurate results in comparison to have a smaller grid, where the smaller grid uses maybe much more compute time than just this 20 times execution of this one here. Of course, the size of n, they always want to have it pretty big. Usually it's in the range of several dozens. Sometimes they say it would be nice to have 150 or so, but we don't have the computational power for that. So we started with a program that was executed in ensemble mode. And we did the following thing. We ran the program in ensemble mode and got from these ensemble members a set of results. Then we took one random ensemble member and put this ensemble member on different machines and ran that ensemble member on these different machines. So we got another set of results, which is just from the different computers. And then we compared the variability of variables on these different computers with the variability of the same variables on these ensemble members. That was done by a colleague of mine a few years ago. The results are not really a proof of something special. It was just to get an insight of what happens once you change a machine. Because we had a change of the machine in 22 in the beginning of the year. And then, of course, there's a lot of crying with the computer scientists to say, oh, yeah, you have a new machine. Fortunately, I mean, we went from Intel to AMD. That was not so heavy. But before, we went from PowerPC to Intel, and everybody said, oh, okay, different mathematics. We wonder what this will have an effect on the results of our modeling. Yeah? So there was a lot of crying about that. And so the question here for that research was, what is the variability of these variables if you make ensemble mode? And what happens if you change the machine? Will it be in the same range? Will it be less? Will it be more? Should we be afraid of changing the machines? And what Beate Geier, that's her name, a colleague of mine, what she found out is that this is in the same range. It's not a proof, but I will show you the details. So what we did is, what she did in the end was she used Cosmo as a program. She produced she ran it on the CSCS computer with 6 ensemble members. That is small, of course. But then she took one of these members, ran it on 6 different machines. Got 6 different results, so to say. And then we compared the 2 sets. And what you see here is, she did that with several variables and several locations. This is the location of Oslo in that climate modeling. This is the days of the year, so it starts somewhere in the middle of the year, goes till the end of the year. And what we see here in the first graph is the deviation from ensemble mean in temperature for this time ensemble. So you have 6 ensemble members, you run them for the temperature of Oslo, yeah, and then you see, okay, during summertime there's not so much variation between these ensemble members. Pretty nice mathematics also in the end, but then it gets a little bit more tricky. So between the ensemble members, is more variation for this latter part of the year, which usually is triggered by the fact that there are more changing weather situations towards the end of the year, and then the power of prediction that the individual members have is a little bit less, it's a little bit reduced. So the members, if you compare the members, then there's more variation between the individual members. So then we ran this on the 6 computers, and we got a result that pretty much looked the same. So the scale is also the same. And this is then the variance of both sets. So what she found is that the variance of this, she did it with several variables, of course, and many locations, not just Oslo only. The variance of what the ensemble members bring to you run on a particular machine compared to running one member on 6 different machines, yeah, and taking that as a set of ensembles, the variance is in the same range. And it's astonishingly pretty close to each other. Yeah. There's no argument why this is the case or whether with other experimentations this can be repeated. Yeah, it was just an investigation. And this investigation shows that if you change the machine, nothing more happens than just if you change your ensemble members. So you must not be afraid of changing the machine in that particular research. Yeah. So finding is what I said, the variability is between the computing of the ensemble members and changing of the platform is more or less the same, and you don't have to fear the change. In general, it's nevertheless a problem because they always say, okay, if you, DCAR said, if you change the computer, then we have to re-investigate all our research and see whether we will get similar findings with the new computer as the ones that we have with the old computer. An ironic side note to this investigation, because she did that some 6-7 years ago, you could not repeat it because none of the computers does exist anymore. So bad. But that means if now, that's good. If you look at this ACM classification, then this refers only to repeatability and reproducibility, not to replicatability. So if you have another 6 computers and another group that picks up the idea of Beate and runs it on one computer and 6 other ones, presumably we'll get the same findings. Yeah? That would be great. So someone should perhaps try it. Okay, I once gave that talk at a conference where there are people from automotive, from HLRS, Stuttgart, you know, and the automotive people, they said to me, well, we never get the same results, but we just don't care. It's car construction. So if you ever wondered why sometimes the door of your car does not close properly, for example, it might be because of this. A certain attitude of engineers. And of course the problem, I mean, there's really from the science that is conducted, there is a difference between automotive and climate, because climate has enemies. And having enemies means that you have a much higher degree of quality control in your scientific results that you just do with these cars, because you produce them, you sell them, and then it's the buyer's problem. But with climate science, with having people who have political power who doubt in general that it is triggered by human beings, yeah, you must be very sure of what you tell them. And if you have this non-reproducibility issue in your programs, that is a problem, of course. Some observations. Bitwise reproducibility is, this repeatability in particular, is very difficult to be implemented. We would like to have that for debugging purposes, for example, just that you can rerun the same path through a program several times. That means you cannot have load balancing, optimized libraries is a problem, high compile optimization is also impossible. And still, even if your program is repeatable, yeah, it's not necessarily reproducible by others, because others will not have the same libraries, will not have the same computer. And even if they have, there might be a problem that it's not replicable, because you publish your paper, and then in the paper is written something. So if another group wants to pick that up and repeat or replicate your investigation, might be very complicated. That is now that is now very tricky. I think in computer science, we are somehow in some points we are a little bit advanced. Just, I don't know who of you is aware of these ACM badges that you have with the publications, yeah, that you have reproducible results, blah, 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 all these things, very complicated. I recently met one of my students who is into, some students who are responsible for, who is studying medical science, and she said that if she wants to make a PhD in medical science, then on such a public server, somehow she has to register her scientific questions before she starts doing the research. Then she does the research, and then she's allowed to write a thesis about what she found concerning those questions. Because I mean, you know how it happens usually, huh? You do some research, you find something, and then you said in the end of your research, you say, my questions, by the way, were just those, which I answered here with this text that I provide. No, nowadays they have to register the research questions before they start with the research. So everything is now much more complicated as the time when we all did that. And this is connected to this issue, of course.
And somehow the bad news is that you're looking at the easy problem. As soon as we throw machine learning,
yeah.
I mean, nobody knows what those models are doing.
Yeah.
They're doing amazing levels of linear algebra, statistical calculations. And we're throwing that at science.
Yeah.
We're doing more and more science based on.
That would be a good topic for the evening dinner part. Yes.
But seriously, these are fantastic studies, and it's really nice to see this so carefully quantified and see all these pressing limitations. But the world has gone crazy with these machine learning environments now.
Yeah.
So what does that mean at all for science?
I think it's a completely different topic here, but let me just say something that is on my last slide. I have a list of things that will make it more complicated. Machine learning is on the list, of course, because it's not only that it's not reproducible in most cases, it's also not understandable. The non-reproducibility, by the way, is not necessarily an issue because you would be able to write all these things in a deterministic way. And if you do a deterministic training of the network, then if you do it 2 times, it might be the same afterwards. Let's discuss this during the evening. But the non-explainability, that is the next point. Okay, I asked my people from Max Planck, so provided that you can produce a bitwise reproducible program, why do you want to have this? And then they said, yeah, they would like to find errors in the parallelization because then you can do a proper debugging, as we all know, of course. And they would like to understand influences of changes with compilers and libraries. So if they write a reproducible program and we change the machine, then they do an evaluation of their results. And they can say, okay, this is now another result because DKZ bought a new machine or it's a new compiler. And they do careful evaluations of our changing hardware, software environment. And it's necessary for them to understand which changes on our side trigger what changes on their side. Now, why would someone else run a program that is bitwise reproducible? And by the way, the funny thing is, everybody speaks about reproducibility, but nobody speaks about reproducing. Because if you run a program, let's say you have a big climate model, costs you 100,000 euro for electricity, who would really be willing to run it another 5 times just to find out that, yeah, it's reproducible? Cost you 500,000 in addition. Who and why? Well, there are no answers to this, yeah? And also for me, the most important point in that whole game is the question which progress in mankind was really based on the fact that something is reproducible, or which, let's say, fraud was detected because it was non-reproducible or whatever. So the justification of having all this effort, I mean, just imagine these ACM badges, these people who do the reviewing of reproducibility. I will never be one of them. I retire early enough. But it could hit one of you then. That's a lot of work, yeah? In Bavaria, there is a saying that I translate here to English literally. That is a saying which says, weighing the pig frequently does not make it fat. And it's just like this. There's this hubris of reproducibility wishes where there is no clear verification why we should do that. Of course, we will have better science, but why should we do it? And who the heck will pay for that? Keeping the data that are produced for decades, keeping next up. I mean, when we published something in our younger days, we published it, and it was gone, it was published, and it was fine. Then you had to keep the data. Now you have to keep the programs. I just wait for the day when they say, please keep the machine that you did it on. Yeah? So we make some archive of these machines. I mean, this is crazy. And it changes, it gets worse every few years. Okay, my personal observation, it will only be worse then. Exascale will intensify the problem. Data intensiveness will, machine learning, as we said, will make it terrible. And we get more and more results. I mean, the point is always, listen, I mean, we get more and more results. Who is the group of people who will run after finding out whether these results are reproducible? And why should we do it? I mean, there will be wrong results. We came up to that point, mankind, to 2024. We have a lot of nice things around us, and we for sure have many fraudulent results, wrong results, whatever, and nevertheless there's progress. And we hadn't had all this reproducibility discussion a decade ago. No? So the theory of science foundation is unclear, in my opinion.
You can add quantum computing there.
Oh yes, quantum computing, yeah, exactly. So science needs to investigate the issue of how to evaluate correctness and validity of results. This is clear, of course. Whether this is the right way with badges and all that, I don't know. We see more and more workshops. I was last year on a workshop in Santa Cruz, the first workshop on reproducibility. Unfortunately, it was a bit unfocused. So they had several people spread over these abstraction layers that I showed you in the beginning. And the discussion was not that good. But there are more and more discussions we see usually during supercomputing, 3, 4, 5 talks, workshops, groups, concentrating on reproducibility issues, which in fact is good, but you must not exaggerate that, in my opinion. Yep, thanks for your attention.
You know there was the Journal of Irreproducible Results.
Yeah.
It was founded in the 1950s as a humor magazine.
Yeah.
And it went offline about 5 years ago.
Okay.
I think maybe it's time we have to revive that as a serious scientific journal.
A comment of mine. Before something can be reproducible, the machine sometimes very hard. But my experience in the last 5 years, we do a lot of scheduling research. We always try to find like the 3 best competitor works. So I did that 2 times. 6 different groups, very recent work. Software there, data there, but they simply don't give it to us.
Yeah,
All academic
exactly.
research didn't mention that.
Yeah.
And it's outrageous.
Yeah.
And half of them do not answer, even if you send 6 emails.
Yeah.
It's, these are not exotic universities. They do not answer. The others say, well, I probably think of commercializing it.
Yeah.
I mean, no one commercializes a scheduler for data. No one. Not this academic work. The 5th one said, well, the code is in India and I go home there on Christmas, so don't give it to... It's unbelievable how hard it is to get the sources of academic research that has no chance for commercialization. You don't get the use cases, you don't get the data. This is the biggest pain I have. So I do not even get to a stage.
Right.
To try
There's a nice paper on this from a person who tried to reproduce something like 200 results, contacted the authors. Most did not answer. For those they answered, sometimes he couldn't get the code, or he could get the code but couldn't get it running, or he could get it running but didn't get the same results. So there's a lot of research available about that, what you mentioned here. And then there might be, if it's, let's say, if it's biology or so, there might be patents. So I would like to win a Nobel Prize with my results, whatever. They will not publish it.
Yeah, this is clear.
Yeah.
But the work, we do commercialize that.
Yeah, but that is one facet that is annoying too.
Yeah, but I think for if you are somehow connected to organizing workshops, conferences, journals, I think we should insist we don't publish if you don't open your sources for this algorithm and the data. I think you should insist on that, unless they have a very, very good reason not to do it.
But this is what the batches are for.
Yeah.
Batches, you have to provide, or this is a reproducibility appendix thing where you have to provide all the data sets.
But it needs human effort to check it, and it's not an easy
At
thing.
the conference, they do not enforce that.
Yeah.
So we have to enforce it.
So,
SC goes at least so far to say if you cannot get the best paper award if you don't have one of these appendixes.
Right.
So, just to put in the US view of this one, there's some discussion about this, and actually it came out of Pittsburgh, out of a colleague of mine, so I've been talking to them for a while. The comparison is interesting. Forget about computer science for a moment. NIH funding, so National Institute for Health, mandates, and this is similar to what you were saying about medicine in general, that once they have a data set, for example, that they were collecting personalized data and so on, it goes on a server before any publication. It has to be made available. Now there are safeguards, of course, if it's personal data, not everybody can get access, but the data is in some space that actually others could use, and this is very important for medicine, of course, for other reasons. Now, so there's a push by NSF now that they're saying it's tied to your funding. You absolutely must provide artifacts and make them available, and data as well. However, it's not enforced. And my belief is if you tie it to funding and enforce it, that's the best way of doing it. So for example, right now what NSF is doing, they also have a problem that we don't turn in our reports in time. They're saying if you have one report that's not turned in time, and you have a pending proposal, it gets recommended, it cannot get recommended for funding. Right. Absolutely can. I mean, you're basically blocked out, and they could do something similar like that. That's even stronger than the publication venues, because the publication venues, I can see the authors go like, yeah, give me a little more time, and then the conference comes, and they give the talk, and nobody cares anymore. So, yeah.
But the proof for what this is really necessary, for which progress in mankind and science this is really necessary, this proof is not there. This proof is not given up to now. That we need that, and we need it to this extent. And that we need it, and that we need it to this extent, what you mentioned here. Because, I mean, look how far we came without doing it.
I mean, my argument is there's nothing wrong with it. I do a code walk.
No, just, yeah.
I do a code walk with new graduates. I'll actually do a personal reproducibility study where I clone a thing and we walk through, and I want to see, basically, I want to see that graph in the end. I want to see the entire workload against me to that graph.
Yeah.
And so I'm pretty convinced it's there.
The point is just as you, yeah, I agree with you. The point is just it needs human effort to do all this verification, and the funding parties are not willing to pay for that. I mean, who is doing this badge system? It's just some scientists like us who say, well, this is self-organizing of science, but it's a lot of bureaucracy.
Yeah, absolutely. So one extreme, it's not new. One extreme of this reproducibility challenge or failure is what happened maybe 20 or more years ago with the cloning, Dolly the sheep. Do you guys remember Dolly the sheep? Any successful reproducibility of Dolly? No. Now, what Thomas is talking here about is something very interesting. I'm trying to understand a little bit better, but it is a real-time phenomenon, which is whether it is a real time. We don't want to see the weather forecast for yesterday. We want to see the weather forecast for tomorrow, for next week, or for the next month. So it is time critical. So And because it is so changeable, how one can think about reproducibility here? What I
You know the yeah.
let me just give. What I remember talking to colleagues in the European Weather Forecasting Center in Reading years ago, but it is fascinating that they already had a database. So whenever the result is unstable, they don't like it, they've got a small window. It has to be the forecast for tomorrow still, but you've got a small window to go back and check what happened 20 years ago, and then you say, well, it's not good, it's not a very reliable what I see for today, but it's similar to 20 years ago, so let me forecast the same thing.
Yeah. And I think it all comes to the point that, as you has an example, medical science, for example, then if it's important for mankind, then you should do this quality guarantee. I always make this joke to my students and say, you know, the physicists who do this galaxy collision things, I mean, if it's more like this or like that, who cares? Yeah. But if in Hamburg you raise the elevation against storm flood, it's an issue whether it's 9 meters or 9.5 or 10. Yeah? And it is based on results like these, and they should be valid in a way. And if it comes to medical science, I mean, in medical science, the FDA regulations were much stricter already in the past. You have to write down everything that you did.